Hi, Miss Nikki here. Welcome to Chapter 2. We get to talk about everybody's favorite topic, chemistry. I know a lot of people see this chapter and kind of start freaking out a little bit. We really have to just understand some of the basic chemistry principles because, like I mentioned in my orientation, we're layering, right? We're building a foundation. I can't talk to you about sodium and potassium ions causing a resting membrane potential, which is what allows muscles to contract, if we have no idea what an ion is, right? Or if we have no idea that sodium is an element or that potassium is an element. So we're not going to teach this at the chemistry level. We're just teaching this as, why are these ions important? What are chemical bonds? What do we need to know so that we can understand some of the fundamental concepts of anatomy later on in the semester? First definition here, matter. So there are three forms of matter. There's solid, there's liquid, and there's gas. Most of us know this from high school or before. I like how they give us examples that directly relate to anatomy. But also remember, we humans are made of matter, right? So the entire organism, we take up matter, right? We occupy space and we have mass. An atom is the smallest particle that exhibits the chemical properties of an element. So I'll show you a periodic table, and then we'll talk more about atoms and subatomic particles. Here's a periodic table of elements. The elements that are highlighted here in different colors are the ones that are most important in biology. So you might see somebody say the word chnops. So this is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the ones that are the most important. And then some of these others are going to play a role down the road. So sodium and potassium are going to help us with muscle contraction. Calcium, obviously bones. We need calcium for bone growth. And then iron here is going to play a role in carrying oxygen in your blood. So these are the ones we'll focus on, but there are some other elements that are pretty important to biological systems. So if we have an atom, and this is the smallest particle of an element, within that atom we have these subatomic particles. So we're going to have protons, which are positive. We're going to have neutrons, which are neutral. And then we're going to have electrons, which are negative. And the electrons are usually orbiting around the protons and the neutrons. When you look on the periodic table, you saw kind of these blocks, and it would have a letter, and then it would have a number at the top, and then a number at the bottom. So the chemical symbol is that letter C. The atomic number is the number at the top, and it is the number of protons. So something to point out, you'll never see this. Carbon has 6 protons, so you will never see a 7 above it. If there was a 7 above it, you'd have to move over one. Go back and look at the chart. What has 7 protons? That would be nitrogen. So the proton number is very specific to the element. Then it has the average atomic mass. So that's why it's kind of not, it doesn't just say 12, it says 12.01. We'll come back and talk about isotopes and how this neutron number can change. And that's why we have kind of this, not whole number, we have this decimal. So the proton number is the atomic number. If the atomic number is 6, then you have 6 protons. If the atomic number is 7, then you have 7 protons. The neutron number is the atomic mass, that was that 12.01 at the bottom, minus the atomic number. So in this case, it's 6. Just be careful, it's not always these nice even numbers, right? Electron number is equal to proton number. So if there are 6 protons, there should be 6 electrons in a stable element. So we're going to see some examples where if you have 6 protons, you might not always have 6 electrons. Elements can give up electrons, or electrons can be removed from an element depending on the situation. I know that sounds confusing right now, but Hopefully I'll make more sense down the road. Just give me a few slides. Let's look at this quickly and just do a couple of the real important biology ones. We already have done carbon, but let's do it again. So carbon, how many protons does it have? If the atomic number is 6, that means you have 6 protons. And we said protons are equal to electrons. So if I have 6 protons, how many electrons do I have? Good, 6. And then how do I figure out neutrons? Neutrons is atomic mass minus atomic number will give me the number of neutrons. And I always write these designations off to the side just because it helps me keep everything straight. Again, don't be lulled into a false sense that they're all going to be the same numbers, right? You can't just say, oh, they're all 6, so that's how it works for every single element. It doesn't, right? All right, let's do nitrogen. These are going to look very similar. You're going to be like, Miss Nikki, you're lying to us, right? We can do another one. I'll show you hydrogen in just a second. So nitrogen, I'm going to pull it out here. Nitrogen, let's do protons. Number of protons is equal to atomic number, so there's 7 protons. Protons are equal to electrons, so there's 7 electrons. And then neutrons is equal to the atomic mass minus the atomic number, so there are 7 neutral neutrons. All right, let's come over here and look at hydrogen. So protons are equal to atomic number, right? So what's the atomic number? 1, right? So you have 1 proton. So how many electrons do you have? 1 electron. Good. Okay, now neutrons. What's the atomic mass? Atomic mass minus atomic number. Well, that's how many neutrons. We just say 0. So how many neutrons? 0. So hydrogen is really just 1 proton and 1 electron. So now comes the fun part. The electrons are the parts that are out in these energy shells, and they're the ones that are causing reactions to happen. You can see the protons and the neutrons kind of stay bundled on the inside. These electrons are in these energy shells, and these electrons are what's causing elements to be attracted to each other or repelled from each other, creating chemical bonds, breaking chemical bonds. So what's going to happen is the very first shell can only hold 2 electrons. So I'm going to go back to a different color here. So here's the first shell. The first shell can only hold 2. The second shell can hold up to 8 electrons. Just depends on how many you have. So this one has, and there's more shells. There's a third shell. We could keep going. So if you have an element that has 8 electrons, and if you go back and you look at your periodic table, that should be oxygen. So you're going to put 2 electrons in the first shell, and then the remaining electrons go to the second shell. So there's 1, 2, 3, 4, 5, 6, 7, 8. What did I say the last shell can hold? It can hold up to 8. So it's almost like there's a blank spot here and there's a blank spot here. Oxygen has room to hold 2 more electrons. Here's the term I talked about earlier, isotopes. So sometimes different atoms of the same element can have differing numbers of neutrons, and that causes changes to the atomic mass. So we have carbon 12, carbon 13, carbon 14, and the neutron number changes. Remember, the proton number cannot change. If the proton number changed, we're not carbon anymore, right? So the neutron number is changing. And this has to do with cosmic radiation. It's probably more than I want to get into, but there are times that neutrons can be excited and they can bombard elements and they can cause changes in elements. And that's kind of how we get carbon-14. This is also how they do carbon-14 radio dating, right? They can look at the amount of carbon-14 in something versus the amount of carbon-12. This is kind of the stable form of carbon, the one that we're most familiar with. And all carbon-14 usually and will eventually break down into carbon-12. So it'll lose these extra neutrons, trying to get to its ideal stable state. The next slide is really what you'll have to know for allied health. So this I just gave you a little bit more information than you probably need. Isotopes, they're elements with different numbers of neutrons. So this is how we use isotopes in medicine. We're going to give you a radioisotope, and it is unstable. It wants to break down to its normal stable element. So we give you a radioisotope, and they release high levels of energy, and we can capture this energy and we can see the organ or the cells within the organ. So this is how we do radio labeling imagery. So just a little more information about the periodic table. These groups here are trying to let you know how many electrons are in the outer shell. So they call those valence electrons. Remember, the first shell had 2, the second shell can hold up to 8. Well, what happens if you only have 6? Those are valence electrons. And remember, I said these electrons are the things that are going to interact with each other, right? They're going to cause chemical reactions to happen. They're going to cause bonds to form. So here in this column, we have 7. There are 7 electrons in the outer shell. So if you already have 7, I'll draw another one here. If you already have 7, it's probably real easy to take one more on, right? If you get one more electron, then you're happy, you're at 8, right? What about over here? If you have 2 electrons in your outer shell, it might be easier to get rid of 2, right, than to take on 6. So just trying to give you a little bit more information. What you need to focus on is that the electrons are kind of what's causing reactivity, and the valence electrons will tell you how these elements are going to behave, how they're going to bond to each other. And we're going to talk about ionic and covalent bonding in just a second. When an element gives, or an atom within an element gives up an electron or takes on an electron, it then becomes an ion. So you might have seen this, or this, or this, or this. If it has a plus or a minus, that's telling you it's an ion. And I like to think that these are the elements, or the atoms of the elements that are doing the most work. So if you see something that has a positive or a negative next to an element name or an atomic symbol, this is probably significant to some sort of physiological function. Let's look at an actual example of forming ions, right? And then how those ions can form ionic bonds. So here we have a sodium atom, and sodium had 11 protons, therefore it had to have 11 electrons. Remember, the first shell fills in 2, then we go to the next shell that can fill up to 8, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 2 in the first shell, 8 in the next shell. We've got a total of 10 electrons. We have one more, so we have this one lonely electron in this third outer shell. Along comes a chlorine atom. I'm not going to count all 17 of these. Look at the very last ring, 2, 4, 6, 7. So do you see how chlorine has a blank spot, right? So when you take a sodium atom and a chlorine atom and put them together, the sodium atom is going to donate the electron, that one lonely electron, to the chlorine atom. And now we call it chloride. And you see how the designation changes. It's not just Na or Cl. We let you know that it is slightly positive. So this is important. Why is it slightly positive? So these are the why questions that we have to keep asking ourselves, right? It's not just rote memorization. Why? Understand why. If I had 11 protons and 11 electrons, do I still have 11 protons? Yes, I have to, right? If the proton number changes, the element changes. All right, but what about the electrons? We gave one up, right? What did we do to this electron? We transferred it over here. So now we only have 10 electrons. You can go ahead and count them up if you want. So what does this mean? I've got 11 positives and 10 negatives. That means I'm overall slightly positive. That's why we put the little positive right there. What about this chlorine atom that changed to a chloride ion? So it had 17 protons and it had 17 electrons, but then it gained one electron, right? This electron from the sodium was transferred to the chlorine atom to make it a chloride ion. So now I have 18 negatives. So this one is overall negative. This one is overall positive. So this is how ions work, and this creates an ionic bond. They are locked into an interaction with each other, and we call that an ionic bond. Next, we have covalent bonds. So just to kind of recap, ions is where we transferred electrons, right? And you have this positive sodium and this negative chloride, and they're kind of in association with each other. Covalent, you're going to share electrons. So let's look at some examples. We're going to specifically talk about these sugars in part 2 of chapter 2. So if you see a structure like this, they're trying to tell you that these are covalent bonds. If you see something written this way, they're telling you covalent bonds. We'll talk about these sugars a little bit later, but they are covalent bonds, and they always, if it's a sugar, it has this 6 carbon, 12 hydrogen, 6 oxygen structure. So you're going to see 6 carbons, 12 hydrogens, and 6 oxygens. And these are sugars because they end in ose. This slide is kind of just thrown in here. We'll come back and visit this when we do the second half of part 2. I think they just wanted to expose you to sugars before we move on to covalent bonds. I went straight to the figure. Please go back and read those 2 previous slides. You can always hit pause and kind of read it at your own pace. I like to come straight to the figures here, though I think sometimes it makes a little bit more sense when we're talking about bonds. So do you remember hydrogen? So hydrogen had 1 proton, it had 1 electron, and it had 0 neutrons. So if hydrogen has 1 electron here and 1 electron here, this is only 1 shell, right? Hydrogen only has 1 shell. This shell likes to hold 2 electrons. So instead of donating electrons, they can do what? They can share them. So covalent is sharing of electrons, while ionic is transferring electrons. Here's a double covalent bond. With oxygen, you've got 2 in the first ring, and you've got 6 in the outer ring. 1, 2, 3, 4, 5, 6. Same over here, right? 1, 2, 3, 4, 5, 6. If they share all 4 of these, do they now have 8 electrons? Yes. So they're sharing. And you can also have a triple covalent bond. All right, let's look at covalent bonds specifically of carbon. So if you remember, carbon look like this on the periodic table, right? It has 6 protons, it has 6 electrons, and it has 6 neutrons. So those 6 electrons, you're going to have 2 in the first shell. 2 minus 6 is 4. You're going to have 4 in the second shell, and that's telling you it's going to want to share 4 electrons in order to satisfy that magic 8 number, that octet rule. So you'll see that carbon will usually bond, covalently bond, share electrons with 4 other atoms. In this case, it can form a double bond, and then it can share with 2 oxygen atoms because everybody's 8 is satisfied. So I could do this in another color, and I could say, okay, there's the 2 on the 2, 2, 2, 2, 2. Now go to the second one. If everybody's happy in this structure, then we should have 8. 1, 2, 3, 4, 5, 6, 7, 8. So carbon has these 4, and it has these 4, and it's sharing them with 2 oxygens. So everybody's happy. The 2 oxygens are happy, the carbon is happy. So what's interesting is you can look at valence electrons, and it'll tell you how many atoms are going to bond or bind to the atom that you're looking at. So carbon is very versatile. Carbon has 4 electrons, and it wants to share 4 electrons with 4 other atoms. So you can make all different types of structures with a carbon skeleton. So you can see this is like a straight line, right? You can make a straight chain with carbons with hydrogens hanging off. You can make branched chains. You can create ring-like structures. So the electrons, the state of the electrons and the state of the outer ring of carbon allow it to be very versatile, so we can form many different structures. I really just want you to focus on the polar and nonpolar. So these are still covalent bonds. We're still talking about sharing electrons. But what's going to happen is sometimes if you have unequal sharing, it's going to shift the molecule that's created into one side's positive and one side's negative. So this term polar, I just want you to think opposite, unequal sharing. So in this case, oxygen is overall negative on one side because it's got these 2 hydrogens bound. Remember, we're sharing electrons here, but this side is overall positive and this side is overall negative. So this would be a polar covalent bond. If you have equal sharing, that would be like the carbon and the hydrogens. So this would be nonpolar. Everything is shared equally across the molecule, so there isn't one side that's more positive than another. So like we said with ions earlier, this dynamic is probably going to cause something to happen, right? Where this is really pretty stable, you may or may not have any interactions. So define covalent bond, define nonpolar covalent bond, give an example, define polar covalent bond, and give an example. The last type of bond is a hydrogen bond. So we talked about ionic, that's transfer of electrons. Then we talked about covalent, that's sharing electrons. And now we're going to talk about the third type, which is hydrogen bonding. So what's going to happen is you're going to have interactions. Remember, this side is negative and this side is slightly positive because water is an example. This is oxygen, hydrogen, hydrogen. That's H2O. That is water, right? So this is an example of a polar covalent bond. What happens is we're going to see the properties of water. This negative side of the water molecule is going to be attracted to a more positive molecule someplace else. So we'll look at these hydrogen bonds in more detail. Here's our nice, kind of looks like Mickey Mouse, right? And it always makes me laugh. So you can see the sharing of the electrons here and here. And then you can see that there's more electrons on this side. There's 6 electrons on this side, and there's only 4 electrons on this side. So you can see that this side is more negative, and this side is more positive. So these hydrogen bonds, the water molecules will have this orientation where the negative side of the oxygen is attracted to the positive side of the hydrogen of other water molecules. So the ability for water to kind of stick together to form droplets is because of the polar nature of the water molecule. Here are the phases of water. Most of us know liquid water, solid water is ice. When I think of gas water, think of water vapor. If you want to think humidity, right, the amount of water that's in the air. Liquid water within the body carries out many functions. So it can transport, right? Many substances are dissolved in water. When I think of transport, I usually think of blood as well. Blood is one of the largest components of blood is water. It can lubricate, it can reduce friction. We talked about that, those serous membrane layers and serous fluid. That serous fluid is made up mostly of water. It acts as a cushion. So we have things like cerebral spinal fluid that we'll talk about when we get to the brain. This acts as a cushion for the brain. This is made up mostly of water, right? You could think spinal fluid protecting around our spinal cord. Secretes waste. So again, in order to get rid of waste within the body, we need water. So cohesion, these are all properties of water. Just like water is polar, that was a property of water. Now we're going to talk about cohesion, surface tension, and adhesion. So cohesion, water sticks together. Remember, you have the hydrogen, the oxygen, and this is slightly negative, and then you have the slightly positive of another water molecule, the hydrogen, which is slightly positive. So water molecules like to stick together, and water molecules are attracted to other substances. So you have your water molecules sticking together, and then you have water molecules sticking to other surfaces. So if you ever have I'm not going to draw, y'all, I'm not an artist, right? Here's our water bottle. You have water in your water bottle, but then you might also have a drop of water stuck to the side of the bottle. So water not only sticks to itself, but it sticks to other or is attracted to other substances. Surface tension, the inward pulling of these forces at the surface of the water. So if you have water here, the water molecules are trying to stick to each other, and that forces them to be kind of really dense right here at the water level, and that creates surface tension. So you can have, think about a pond, and you have those little bugs, those little water striders that can sit on top of the water, right? They're distributing their weight enough, and the surface tension is high enough. So this might not sound, you're like, great, okay, water sticks together and water sticks to other things. But we need water to break down chemicals in our body. So this is a really good thing. Some more properties of water we have to talk about are high specific heat and high heat of vaporization. This has to do with kind of controlling body temp, and this one has to do with sweating, and this is going to be on the next slide. So the high specific heat that water has is due to the energy needed to break all those hydrogen bonds. So water is going to cool slowly, and it's going to boil slowly. I think the best example of this is if we talk about the oceans. So imagine you've got the sun, and the sun is shining down on the water, right? The water is going to heat up really slowly during the day, and then when the sun goes away and it's nighttime, the water is going to cool down really slowly. This allows for more regulation. Do you want the oceans to be boiling at noon and frozen solid overnight? No, probably not. Probably the same with our body, right? We don't want all the water to be boiling 1 second if we step outside and it's 110 degrees outside, right? So this high specific heat allows for more regulation and more control in keeping a regulated body temperature. So heat of vaporization, we kind of already talked about, right? So heat of vaporization is that idea that you have sweat, and as the sweat cools, it draws heat away from the body, and that cools you down. So excess heat dissipated as water vapor. Another property of water is that it is the universal solvent. So solutes are the substances that are dissolved. Solvent is the item doing the dissolving, and the result is a solution. So again, if I had solute is salt, solvent is water, what's the resulting solution? Salt water. Pick something else if you want, right? So solute is chocolate, solvent is milk, solution, chocolate milk, right? Water is the universal solvent. We dissolve most of the substances within our body, it's dissolved in water. And then we can get rid of the waste in our body via it being dissolved in that water. So we'll talk more about that when we get to urinary, but that might be a little while. Substances are going to interact with water differently. So hydrophilic, water-loving. You can put glucose in water. It doesn't mind the water, but it's going to remain intact. The water cannot get in between these bonds and start breaking them. So glucose will be found whole, all in one piece inside water. Then you have some electrolytes that'll totally dissolve and disassociate. So here we have sodium and chloride. When you take that sodium, positive sodium, and that negative chloride that are attracted to each other, if you take this and drop it in water, they're going to get pulled apart into their individual ions. So you should be able to see here the difference in terms of bonds. Glucose was a covalent bond. What was sodium chloride? Ionic bond. Good. You have some hydrophobic, water-fearing. Think of fats, right? We call them lipids in biology, but fats don't like water. Fats will form little fat droplets or particles to get away from water. And then you have some molecules that will partially dissolve in water. Water will spontaneously dissociate to form ions. So if you have water here, and I throw in some sodium chloride, that's really salt. Let's say I throw some salt in. What's going to happen? Well, two things. One, the water can wedge between the sodium and the chloride, and you'll have sodium ions and chloride ions. What can happen is the water can also disassociate. So you have your water molecule, it can break apart into hydroxide ions and hydrogen ions. And what is this telling you? What's the negative and the positive telling you? One, it's an ion. Two, it can do some sort of interaction. If it's positive or negative, it can go somewhere in the body and cause action to happen. Two, or three, I guess we're on, this tells you that the OH is overall negative. So it must have extra electron. And this one is overall positive, which means it lost its electron. So why do we have to talk about this? Because if water is a universal solvent and we're made up of water, we have lots of disassociation going on. And we're going to end up talking about potential hydrogen or pH of different parts of our body. So we need to know what an acid is, and we need to know what a base is. So in that example, if I have water and I put in hydrochloric acid, I've kind of given it away that it's an acid, right? I put in hydrochloric acid. What does it break apart to? This is going to break into chloride and hydrogens. What's going to happen to the water? It could break down, some of them could break down into ions, right? If you place a substance in water and you have lots of hydrogen ions as a result, that's an acid. So what's a base? Less hydrogen ions. So again, here's my example. I've got water in here, right? Let's say this time I put in sodium hydroxide. I put in my NOH. The water is going to drive these two apart. I'm going to end up with sodium and hydroxide. I have more of these, but that also means I have less of these, right? So this is a base. Sodium hydroxide is a base. I know by now we're at the point, Miss Nikki, why do I have to care about this? Well, the reason is pH is important within the body. If your pH is off balance, it can cause issues with the way that organs function. So if your blood pH is really high, it can cause enzymes to break down and then they can't do their job anymore. In your stomach pH is a pH 2. It's a really low pH. That's so that you can break down food particles. If your pH was really high in your stomach, you wouldn't be able to do that. So pH really is important. I know I haven't explained really why yet, but it's coming up in the next couple of chapters. So just look at this real quick. This is a pH scale. Neutral is about 7. You can see pure water is listed here. Human blood's pretty neutral. Milk, saliva, these are kind of in a neutral range, right? What's acidic? Hydrochloric acid, wine, grape juice. What's something that's basic? You might also hear the word alkaline, but they mean the same thing. What's basic? Sodium hydroxide, bleach, ammonia, antacids. And something to pay attention here, we always associate acid with bad, but we don't necessarily associate basic with bad. But do I want to go drink any household bleach? No, probably not. So we want to stay in this neutral range. Anything above or below, depending on where it is in our body, is not really good. So what does it mean if you're an acid? If you're an acid, you have a higher hydrogen ion concentration. What happens if you're a base? You have a lower hydrogen ion concentration. So think for a second. I know you'll go through some practice problems within Connect, but make sure that you understand that a pH 1 is more acidic than a pH 4. So if I said pH 1 more or less acidic than pH 4. pH 1 is more acidic. What about pH 10 versus 14? pH 10 versus pH 14. Which one is more acidic? This one is more acidic than this one. I want you to just be familiar with these terms, neutralization and buffers. So you can kind of neutralize an acid or a base using a buffer system. We're not going to talk about these till the second half of anatomy. But basically, a buffer can help prevent pH changes. So you know how the stomach had pH 2, right? I said you have hydrochloric acid in your stomach. It's about a pH 2. Your blood, we said from that last slide, is about a pH 7. So when we're dumping our waste from the stomach into our blood to be cleaned, how do we stop the mixing of these two? Right? What happens if I just dump a whole bunch of pH 2 fluid into my bloodstream? That's going to change this number, right? It's going to make your blood acidic. And we want our blood to stay right around pH 7. Remember, that's the neutral. So we have buffer systems, and for lack of a better word right now, it can capture this pH 2 fluid and prevent the increase or decrease in blood pH. It basically stabilizes the pH of the fluid in your bloodstream. So just basic definition for right now. So when it comes up down the road, you aren't surprised. Some expressions when we're talking about concentration. So you could have mass per volume. So you could have micrograms of a drug delivered per liter. That's micro. So this is mass of the drug that we're giving per volume. You can also do mass over volume as a percentage. So if you see something that says 5% dextrose solution, what does that mean? That means you have 5 grams of dextrose per 100 mLs. So it's still mass for over volume, but you're listing it as a percent. Two more expressions of concentration. We have molarity and molality. Molarity is if you have moles of a solute in a solution. You can see here it's per liters. And molality is moles of a substance or solute per mass. So it's measured in kilograms. Okay, more confusing. Why do we have another set, osmolarity, osmolality? We are talking about whether a substance dissolved or not. So you see we're using the term particles. We're not using moles. So I'm going to scratch this out. Go back to molarity. What was molarity? It was moles per liter. What's molality? Moles per kilogram, right? So this is a specific measurement. If I have 1 molar sodium chloride solution, if I disassociate this, I have 1 molar sodium and I have 1 molar chloride. I had 1 mole and 1 mole for this molar solution because I was talking about how many moles do I have. Osmolarity just means particles. How many particles? So if you had osmolarity, particles in a liter solution, if these disassociated, you're going to have a higher particle number. So if it was whole, you'd have 1. If they've disassociated, you now have 2 particles. You have this one and you have this one. So osmolarity and osmolality don't have to do with exact measurements like moles. It has more to do with, did the item dissociate or did it not? So hopefully that wasn't too confusing. I know we have part 2 to go to, so just kind of hang on through these chemistry chapters. I promise you, if you learn it now, it'll pay off when we do muscles.